Hi everyone. Today we are discussing about determination of inverse Laplace transform. In previous class we are discussing Laplace transform. Before we are discussing Fourier transform functions. Now we are entering to the different topic: differentiation of inverse Laplace transform. Differentiation of inverse Laplace transform. First heading is finding inverse Laplace transform. How to find out the inverse Laplace transform? In recall that inverse Laplace transform x of capital X is given by here x of t is the inverse Laplace transform, that is 1 by 2 pi j integration of sigma minus j infinity sigma plus j infinity x of s e of s e power st ds, where re of s is equal to sigma with respect to the ROC of x. Unfortunately, the above counter integration can often be quite tedious to compute. That means consequently we do not usually compute the inverse Laplace transform directly using the above equation. For rational functions, the inverse Laplace transform can be more easily computed using partial fraction expansions. Using a partial fraction expansion, we can express a rational function of a sum of lower order of rotational functions whose inverse Laplace transform. So, the conclusion of finding inverse Laplace transform, we are using x of t formula in different conditions. Next one is Laplace transform and LTI systems. Laplace transform and LTI systems. System function of LTI system. System function of LTI system. Consider a LTI system. Consider a LTI system with input x and output y, impulse response h. Consider a LTI system with input x, output y and impulse response h. Let x, y and h denote the Laplace transform of x, y and h respectively. Since y of t equal to x into h of t, the system is characterized in the Laplace domain y of x equal to x of s, h of x, where h is a system function, x is a input device, y is a output device. As a matter of technology, we refer to h as the system function or transfer function of the system. When viewed in the Laplace domain, a LTI system forms output by multiplying its with its system function. That means when we are calculating system output of LTI system, we are using system input and function of the system h of x. A LTI system is completely characterized by its system function h. If the ROC of h includes the image, then h of s tends to s equal to j omega in the frequency response of LTI system. Frequency response of LTI system. Block diagram representation of LTI system. Already we know input side we are applying x of s, and output side we are getting y of s, and the system function is h of s. Here we are applying x input to y output to, and we are getting y of t function. Since LTI system is commonly characterized by its system function, we typically label the system with this quantity. Next one is interconnection linear time invariant system. LTI means linear time invariant system. Okay, the series interconnection of LTI system with the system function h1 h2 LTI system functions h equal to h1 and h2, that is we have to equivalent shown below. X of t y of t h1 h2, x of t y of t h1 h2. Here we are observing x in x1 into x2 equal to h1 of s into h2 of s equal to h1 of s h2 of s. Now another function is h1 h2 h2 h1 regeneration model, whatever it may be, h1 h2 equal to h1 h2 h1. It is possible to write the equations like h1 h2 equal to h2 h1 h2. So these are the different function conditions. For example, 1 into 1 equal to 2, 2 into 2 equal to 4. Seems like the h1 h2 equal to something. In parallel, introduction of the LTI system within impulse response of h1 h2 is a LTI system function h equal to h1 plus h2. From the above multiplication part to series in the series interconnection LTI system, in the process of series the functions are multiplying. Interconnection LTI system, in the process of parallel interconnection is adding. So that's why h equal to h1 and h2. In parallel interconnection of LTI system with impulse response h1 h2 is a system with the impulse with the system function h equal to h1 plus h2, that is we have to equivalence shown below. So when input side we are applying parallel h1 h2. Now output side we are getting h1 plus h2, h1 plus h2. So these are the two different series and parallel conditions and equations. Why it is like indicating that we can simplifying the problems further communication devices. Next one is causality. A LTI system is causal, its impulse response is causal, and therefore right sided. From this we have to resultant below. So general causality means if a LTI system is causal, its impulse response is causal, therefore right sided. That means LTI system causal, impulse response causal is represents the is represents the represents the image location at the side of right side. Okay, next one is the theorem. The ROC associated with the system function of a causal LTI system is a right half plane or the entire complex plane. In general, the converse of the above theorem is not necessarily true. That is, if the ROC of the system function is a RH or the entire complex plane, it is not necessarily true that the system is causal. System is causal. If the system function is rational, however, we have that the converse does hold as indicated the theorem below. For a LTI system with a rational system function H, the causality of system is equivalent to the ROC of the H being right half plane to the right side of the rightmost pole. H has no poles, then the entire complex plane. So these are all some rules and regulations when we are using causality related applications. Now we are entering to the another one. Bibo stability. Bit in, bit out. Bit in, bit out. Whether or not a system Bibo stable depends on the ROC of its system function. A LTI system Bibo stable if and only if ROC of its system function H includes the entire imaginary axis. A causal LTI system with proper initial rational system function H is Bibo stable is and only if all the poles of H is left left half of the plane. So that means in any topic it will write or it will rule some theorems to execute the data processing in the Bibo stability. In previous also we are discussing invertibility. In previous class also we are discussing invertibility. A LTI system H with the system function H is invertible if the only there is exists another LTI system with the function H in such as a H of S H inverse of S equal to 1. For example, in any problem for H of X and inverse of S is equal to dash. H of S H inverse of S equal to dash 1, in which the case H inverse system is also represents H inverse equal to 1 by S, 1 by H of S, 1 by H of S. These are the invertibility functions in LTI system. System function and differentiational equations. System function and differentiational equations. Representation of LTI systems. Representation of LTI systems. Many LTI systems are practically many LTI systems are practically interested can be represented using an nth order linear differential equations with constant coefficients, and these are the differential equations representation of LTI systems, differential equations of LTI systems. And next one is circuit analysis. Already we know why we are using resistors, capacitors, inductors. In previous class we had discussed why we are using resistor. Why we are using resistor? A resistor is a circuit element that opposes the flow of electric current. Why we are using resistor? Why we are using resistor? It opposes the flow of current. That's why we are using in any electronic or electrical components. We are using a resistor is a circuit element that opposes the flow of current. Already we know equation V of t equal to Ri of t, I of t equal to resistance. An inductor, next one is inductors. An inductor is a element. An inductor is a circuit element that converts an electric current into a magnetic field via versa. An inductor is an element that converts electric current to the magnetic current. And next one is capacitor. Already we know why we are using capacitors. Capacitor is a circuit that stores the electric charge. Capacitor is a circuit why it is used for to store the electric charge. So by using resistor it will oppose the flow of current on the circuit. It will oppose the flow of current on the circuit. By using capacitor, it will store the some energy of the some amount of the current in the circuit. And by using inductor, it will performing or it will convert electric current into the magnetic current. Electric current into the magnetic current. So by using these three electronic elements, and also we are using several electronic elements, which is more convenient to maintenance the circuit operations, at the same time controlling the power levels with the help of and we are also observing these symbols. Resistor I of t, V of t. Here I of t represents the input current. V of t represents the current voltage at the circuit. Voltage at the circuit. And it is the symbol of inductor. It is also current entering to the inductor side, and the voltage varies from the output side. Next one is capacitor. By using capacitor, it will store some little bit of energy to control the flow of circuit. Next one is circuit analysis. The Laplace transform is a very useful tool for circuit analysis. The Laplace transform is a very useful tool for circuit analysis. The utility of Laplace transform is partly due to the fact of the differential equations that describe inductors and capacitors much simpler to express in the Laplace domain Laplace domain than in the time domain than in the time domain. Already analysis of control systems, feedback control networks, these are all we are explaining next class. Thank you.